All right, so now I hope you had a nice break. You got a chance to get up and stretch a bit. So what I have here on the board, just for review, are the three rate equations for heat transfer. So first, we have Q conduction. So this is the rate, watts of heat energy conducted being equal to the area times the thermal conductivity K times the temperature gradient, or the delta T, change in temperature with X. For conduction, we have the rate of convected, for convection we have the rate of convected heat in watts equal to the area times H, the heat transfer coefficient, times the difference between the surface temperature and the ambient temperature. And then for radiation, we have the rate of heat radiated in watts equals the emissivity times Stefan Boltzmann's constant. What is that? All right, you should know that by now. Times the area times the difference between the surface temperature to the fourth power and the temperature of the surroundings to the fourth power. Or we can represent radiation where we linearize the equation using an effective heat transfer coefficient, HR, that is represented as such. So that ends our discussion of the rate equations. We're going to move on now to energy balances. We're going to look at the first law of thermodynamics, and we're going to write it in terms of rate. So we're going to take energy in the first law, we're going to divide it by time to put it in the units of watts. And the reason we're going to do that, put it in the units of watts instead of joules, is so that now when we have these energy components that you'll see in a second, energy in, energy out, energy generated, and energy storage, we can plug in the appropriate rate equation. These equations are also in watts to account for those components of the energy. For example, if energy is coming in, it could be conducted in, it could be convected in, it could be radiated in. If energy is going out, it can be conducted out, it can be convected out, or it can be radiated out. The energy balance. And if you remember anything from this course, remember that the energy must be balanced. We will start all of our analysis by looking at energy, balancing energy, choosing the appropriate rate equations, and then solving the problem. So we have an arbitrary body. We know that within this body we can store energy. We also know that energy can be generated. Think about a nuclear reaction happening in a cavity. Or think about electrical heating of something. That's the generation of the energy. So we have energy that can be stored, it can be generated, but then at the surfaces of this body, we can have energy that leaves it, and we can have energy that enters it. So the first law of thermodynamics says that this energy in minus the energy out plus any energy that's generated equals the amount of energy that's stored. Now you see here I wrote dots, and I didn't write dots. These dots indicate that these are rates. So now I'm going to write the dots here. These dots are what distinguish heat transfer from thermodynamics. By adding the dot, we move from the units of joules to joules per second to watts, which are equal to joules per second. All right, so let's look at energy stored. Energy stored term. So the energy stored, let's say we're going to neglect kinetic energy. So we're going to look at energy stored. So we're going to take kinetic energy and we're going to neglect it. We're going to take potential energy. We're going to neglect it. So remember from thermal, the stored energy is the sum of the kinetic, the potential, the sensible, and the latent. So we have the sensible energy, which is temperature, and then we have the latent energy, which is phase change. So we're gonna neglect the latent energy for now. We're just gonna work with the sensible energy. And the reason we're doing this is because we want to get to a simple form where we're dealing with a static body. There's no fluid moving in and out of the system, and there's no elevation change within our system. So there's no elevation change within our system, then we don't have potential energy. If there's no fluid moving in and out, our body is static, we have no kinetic energy. And we're going to assume that we have a system that has no phase change. So that all leaves us with a system that just has sensible energy. So how do we represent the sensible energy? Well, the sensible energy is basically a temperature. And I'm just going to say what it is. It's the density times the specific heat times the volume times the change in temperature with time. This is what our energy storage term looks like. Our rate energy storage term. So basically, temperature is showing up as we would expect. Now we'll go into more detail about this later, but I want to do a quick sanity check just to show you the power of units. Because one of the things that you're going to want to do in this class is to always track your units like an accountant. Be careful, look at the units when you solve a problem and make sure they match up. Sometimes you can even solve a problem just by doing unit analysis. And there's a nice section in your book that goes over units, and I encourage you to read it. So here, let's look at the units for this. So we already talked a lot about the units of this energy rate being watts. So these units need to add up to watts. So we have density, which is kilograms per meter cubed. We have specific heat. And specific heat basically is the amount of energy required to raise a kilogram of material by a degree temperature. So it ends up with having these units that look like joules over kilograms over temperature, Kelvin. Then we have volume, it's meter cubed, that's easy. And then we have temperature over time. So we have Kelvin over seconds. Now some of you already probably figured out that the units balance because kilograms cancel, meters cubed cancel, Kelvin cancels, and we're left with joules over second, which is watts. So the units work out, and a lot of times you can use these units, especially if, instead, what if we had latent heat thrown into the problem? This latent energy change. We could just deal with the amount of latent energy put in terms of units over time. So don't get too caught up on that now. We're going to go into more detail, but I just wanted to point out here that units can be a powerful tool for actually doing the analysis of a problem, but also making sure that everything is in line. So we're going to finish up here.